You know, we're surrounded by concrete. It's literally everywhere. But we're not here to talk about how strong it is or what color it is. No, we're diving into something hidden, a kind of chemical fire that burns inside every single pore, from a simple sidewalk all the way up to a massive skyscraper.
So let me ask you a question. Picture one of those enormous concrete dams, right? Holding back millions of tons of water. What do you think is its biggest threat? An earthquake? Some kind of crazy flood? I mean, you'd think it's gotta be some powerful force from the outside. But the real answer is way more surprising.
Nope. The greatest threat, it actually comes from within. It's the concrete's own internal heat, a fire that starts the moment it's mixed. And this isn't just a little warmth. If you don't control it, this internal fire can literally tear a structure apart from the inside out before it ever even sees a drop of water. So, how on earth is that possible?
Okay, to get how this is even a thing, we've got to dig into the science. And that means we have to start by clearing up one really common misconception.
Here's the thing. Concrete doesn't just dry like your laundry on a clothesline. Not at all. It cures. And it does that through a chemical reaction called hydration. The second water hits that cement powder, this powerful chain reaction just kicks off. And this is not a passive thing, it's exothermic. That means it is actively pumping out a ton of heat.
Right, so a little heat, what's the big deal? Seems harmless enough. But when you're talking about massive structures, this isn't just a little bit of warmth, it's a huge engineering challenge. So why exactly is this internal furnace such a massive problem?
The key here isn't just the heat itself, it's the rate, the speed at which the heat is released. That's the real villain of the story. Think about it, in a giant dam, the inside core gets incredibly hot, but the outside surface is much cooler, right? That massive temperature difference, that thermal gradient, creates insane amounts of internal stress. And what does stress lead to? Cracking. Catastrophic cracking that can compromise the whole thing. So, what if we could actually watch this reaction happen in slow motion? Well, it turns out scientists can do just that. They can literally map out this entire chemical heat wave from the very first spark to the final cooldown. Inside that gray cement powder, you've got this cast of chemical characters, and you can think of them like tiny little engines. The two main stars of our show are C3A and C3S. C3A, well, that's the sprinter. It reacts almost instantly, kicking out the first, fastest, and hottest burst of heat. Then you've got C3S, the workhorse. It's the one driving most of the early strength, and it contributes a huge amount of heat over the first few days.
And the entire drama of this reaction, that initial burst, the quiet period, the main event, it can all be visualized in a single beautiful graph. This right here is the heat rate curve, and it tells the complete story of concrete coming to life.
So this story unfolds in 4 distinct acts. First, you get the initial burst, just a flash of heat, the second water and cement meet. Then comes maybe the most critical phase for any construction project, the dormant period. The reaction actually pauses. It gives workers that crucial window of time they need to pour and finish the concrete. After that, bam, we hit the main peak. The reaction accelerates like crazy. And finally, you have the long, slow cool down, as the chemistry just keeps chugging along for weeks, months, sometimes even years.
And this really shows you just how fast modern cement works. You know, back in the day, this process was way slower. But today's construction schedules demand speed, so cements are engineered to react incredibly fast. I mean, look at this. Up to 75% of the total heat can be released in just the first week. That's a massive amount of energy in a really short time.
So how do we even see this hidden fire? Well, engineers have some pretty clever tools to track this whole reaction in real time, which gives us this incredible understanding of its entire life cycle.
Okay, there are basically 2 main ways to do this. First, you've got isothermal calorimetry. Think of this as the super accurate, controlled lab test. It uses a teeny tiny sample of just the cement paste and measures the heat directly, so it can capture even that very first initial burst. Then, you've got adiabatic calorimetry. This one is more practical, more real-world. It uses the actual concrete mix that's going to be used on a project and measures the temperature rise. It perfectly simulates what's going to happen on the job site, even if it might miss those first few minutes of the reaction.
Okay, so if we can measure it, that means we can manage it. And this is where engineers go from being scientists, just observing, to being conductors of this really complex chemical orchestra, tweaking the formula to control that heat.
So the first, most fundamental lever they can pull is the water-to-cement ratio.
Now you might think more water equals more reaction, right? But it's actually the opposite. A low water ratio, which is what you use for high-strength concrete, it concentrates the reaction. There's less water there to absorb all that energy, so the peak temperature can just skyrocket from, say, 45 degrees Celsius to a blistering 70 degrees.
But, of course, there's a trade-off. Using less water also shortens that critical dormant period we talked about. The concrete starts to harden up way faster, which means the crew on site has less time to get it placed and finished. It's this constant balancing act between strength, heat, and just plain workability.
The second big lever they have is using additives, and this is where things get really clever. Take fly ash, which is a byproduct from coal plants. If you replace just 30% of the cement with it, you can cut the peak heat rate almost in half. See, fly ash is what we call pozzolanic. It reacts much, much slower. It basically puts the brakes on that initial heat wave and spreads the whole reaction out over a longer period of time.
Okay, so we've been deep in the weeds of micro-level chemistry. Let's zoom back out for a second and connect all this back to the massive structures that actually shape our world.
And here is the most crucial point of all. That heat curve we saw, it isn't just a graph of temperature. It's a strength graph in disguise. The total amount of heat that's released over time is a direct indicator of how much strength the concrete has gained. So by controlling the heat, engineers are literally, directly controlling the development of a structure's integrity.
So, why does all of this matter so much? Well, because understanding and managing this internal fire is what stops catastrophic cracking in our most important infrastructure. It's what ensures the safety and longevity of our bridges, dams, and skyscrapers. It's what lets us build bigger and faster than ever before, all while walking this tightrope between the need for rapid strength and the concrete's own potential to self-destruct.
You know, it really changes how you look at the world around you. A bridge isn't just steel and stone anymore. A skyscraper isn't just glass and concrete. Every single one of them is a monument, not to brute force, but to perfectly, beautifully controlled chemistry.
Which, of course, leaves us with one final question to think about. As our ambitions grow, as we build ever bigger and ever faster, how are we going to continue to manage the powerful fire that burns within?